Hello and welcome to another discussion of Introduction to Astrophysical Fluids. In this part, we continue our discussion of Rayleigh convection. Okay, and previously we saw that how to derive the basic equations or the governing equations for such a system. For Rayleigh convection. In this part, we will see how to solve or how to proceed for an analytical solution of such type of analytical or exact solution for such type of problem. Okay, so these are those two equations which constitute the family of the governing equations for Rayleigh convection. The first one is of course the evolution of the temperature, of course the perturbative part of the temperature. Del T1 del T is equal to V1Z B beta plus kappa nabla square T1. Okay. The second one is del T nabla square V1Z is equal to alpha times G del 2 T1 del X2 plus del 2 T1 del Y2 plus eta times nabla to the power 4 V1Z. Of course, eta, if you remember well, this is nothing but mu by rho. Okay, so here, for example, you can simply take this eta is nothing but mu by rho 0. Okay, or which is also very much close to mu by rho b. Okay, so this is nothing but the coefficient of kinematic viscosity. So finally, in our equations, we can see there are only two unknowns. One is T1, another is actually Laplacian V1Z. Okay, but no, not quite exactly. Just T1 and V1Z, because here there is no Laplacian V1Z. That's true. Okay. So you can see that these two equations, okay, are almost like the diffusion equations, but a bit modified. So the first one is the diffusion equation for T1 if this term is absent, for example. The second one is a diffusion equation for nabla square V1Z, okay, if this term is absent. Okay, so we can, but of course we can easily see that with all these terms present, this one and this one, they are not quite exactly diffusion equations. Okay, but we can finally think of solutions which can be something which look like much, okay, a diffusion solution. Okay, so that's what our next step is, that we now have to propose trial solutions, reasonable solutions for T1 and V1Z. And there can be many possibilities, okay, and people have done a lot of trials and errors. Okay, you can go through the works of Subramaniam Chandrasekhar, so who had done a lot of work on this problematic of Rayleigh convection, the analytical part. Okay, and there you can see that there is a vast and detailed discussion to justify this type of equations, but here we are just saying that there can be many possibilities. One possibility is just to propose normal plane wave solutions as we did for sound waves. Okay, now here what we will do, we will just see that the equations, the solutions for V1Z and T1 have this type of nature, that is some function capital W. So I am just talking first for the case of V1Z. So the solution will be equal to some function W, which is a function W of Z only. Okay, because if something special occurs, that means mostly the convective motion, okay, that will take place along z direction mostly, okay. And then with t there is a change, and this change can actually be easily understood by this type of dependence, so del t type of thing, okay. So maybe, I mean, if you know simply the diffusion type of solution, you can see that this is a slightly more general form of diffusion like of solution for the z and t part, okay. So here we have simply written exponential sigma times t, okay, that is the temporal dependence of the solutions, okay, both for v1z and t1. And if sigma is real, then there can be a possibility of instability, either growing or decaying, okay. And if sigma is imaginary, then of course we can understand that in time that will be oscillatory, okay. Now uh, for x dependence and y dependence, simply we can just, for simplicity, we can propose plane wave type of solutions, okay, both for v1z and t1. For t1, the z dependent function is the theta, is the this capital theta, okay. So you can easily see that other than the z dependent part, this time x and y dependent part, they are the same for the both for v1z and t1. I mean, instead of telling you the intuitive reason for that, I rather try to encourage you to see the form of the equations in, I mean, much more carefully, and try to understand why intuitively these parts. So there is not a hard and fast, I mean, reason for that, because these are all the trial solutions. And finally, if you take these solutions, you can see that the analysis becomes much more easier, and the analysis is much more physically talking, okay. But at least why these parts should be, I mean, these parts are equal, and that can be a reasonable approximation that you have to guess from these two equations, okay. That is a very smart choice actually, and I want you to just think over this point, okay. Now for our case, what we have just said, that if sigma is greater than 0, then the perturbation grows in time, and if sigma less than 0, then the perturbation decays in time, okay. So that is a strict instability, growing in time perturbation, and that is a strict stability, decays in time. Now we are trying to search for the conditions, okay, for marginal instability. That means exactly the condition where the solution is not automatically growing or decaying just due to its explicit time dependence. So that's why what we will do, we say that sigma positive means instability, sigma negative means decaying solution, okay. Actually sigma, it is not actually stability, to be very honest, okay. But if sigma is imaginary, then actually we are talking about oscillations. But in both cases, whether this is growing or decaying, so we can make the marginal part where the solution does neither grow nor decays in time, and that is the part of marginal stability, okay. And or some people say this is the part of marginal instability, okay. And that is because in this case sigma is chosen to be 0 and time independent, okay. So if you just increase the sigma a bit from that point, then the thing is that even the system, so I mean, why, so okay, so philosophically you can see that philosophically both are, I mean, in the case of proper language, both are actually non-stable conditions. But if the solution, the perturbation grows in time, okay, if the perturbation grows in time, just and then what happens that even if you have oscillatory type of solutions in space, this oscillatory type of solutions will actually grow, and that means their amplitude will also grow in time, makes the system unstable. And on the other hand, if your system is oscillatory but have something like a decaying time dependence, okay, then what happens, this oscillatory type of thing will also decay in time, giving you the original state, which was the static hydrostatic equilibrium state, okay, steady initial state. So in that sense, we say that sigma is equal to 0 is the part of the marginal stability, or some people actually for the same reason called marginal instability, okay, beyond which you have the strict instability, okay. So now and our study will be confined within this regime of marginal stability, okay. So if we have marginal stability, then this t dependent part will go away, and we simply have v1z is equal to w of z exponential ikx times x plus iky times y, and t1 will be equal to theta z exponential ikx times x plus iky times y, okay. If you substitute properly these two values over here, then you can see that the final equations will become beta times w plus kappa times d2 dz2 minus k square times theta is equal to 0. Here I have introduced something new, small k, okay, I am coming to that. And another equation will be minus alpha g k square theta plus nu times d square dz square minus k square times capital W is equal to 0. Now this k square or this k square, this is nothing but equal to kx square plus ky square. That is the modulus square of the horizontal wave number. So this is the wave number which is in the plane perpendicular to the convection. Okay, perpendicular to the heating direction, to be very honest. Okay, so I can say that the heating direction is in the vertical direction. Okay, so what they are, this equation with omega, with w and capital theta, they constitute a system of two coupled linear ODEs. Okay, please check these equations, and how to come from these solutions just by replacing those solutions in these equations. How can you get this? This is a very simple and elegant home task. Okay. Now finally, what we have to do, we can go a bit further. We have two equations to unknown, but two equations to unknown. They are of course coupled linear ODEs, second order differentiation. So we also need two boundary conditions for each. Okay, but just one can do one simple thing. One can actually eliminate theta, one of the two variables, from this system of equations. And if you eliminate theta, for example, from these above two equations, finally you get, so you eliminate theta, so finally you get a sixth order linear differential equation, which is nothing but nu times kappa d2 dz2 minus k square whole cube. So d2 dz2 whole to the power 3 gives you d6 dz6 type of thing, right? So you have everything inside the bracket, d2 dz square minus k square, this operator raised to the power 3 times w is equal to minus alpha beta g k square w. Okay. Now if we define dimensionless quantities z prime, which is nothing but z by d, and k prime is equal to k times d. Okay, two dimensionless, one is dimensionless height, one is dimensionless horizontal wave number. Okay, if we define this two, and d is the characteristic length scale for our system, because this is the vertical size of the container. Okay, we finally write the whole equation as simple as in the form d2 dz prime square minus k prime square whole cube times w is equal to minus ra, so ra is a dimensionless number, times k prime square w. Okay, this dimensionless number is known as Rayleigh number, and this is given by alpha beta g d to the power 4 by k by kappa nu. Okay, so there are two things to remember, that Rayleigh number is first of all increases with beta, with alpha, with d, of course with g, but g is considered to be constant here, but it decreases with kappa and nu. So if the system is more and more viscous, its Rayleigh number will go down, and if the system's thermometric conductivity is more and more important, then the system will also have low Rayleigh number. Okay. On the other hand, if you how to say, if you make the temperature gradient, initial temperature gradient very higher and more important, then your Rayleigh number will be important. Okay, so Rayleigh number in such a in some way basically gives you the importance, the effort of the system to make an important temperature gradient by the effort of the system to destroy that temperature gradient. Okay, so you can easily understand that if a Rayleigh number is larger and larger, then the system can be subject to more and more convectional instability, or convective instability, convective instability. Okay, and if Rayleigh number is lower and lower, then the system will efficiently can efficiently repair the effect of strong temperature gradients, thereby making it more and more stable. Okay, this is the qualitative idea, and which is quite correct actually. One can see in the laboratory experiments. Now, for complete solution of this system, okay, we need 6 boundary conditions, because this is a 6th order ODE. Okay, now linear ODE, of course. Now, depending on the different situations, we need different boundary conditions. Okay, so that is something very important. In physics, we can have different type of conditions where Rayleigh convection can be important, and for which we really need different type of boundary conditions. And another discussion, another point where you can actually see the discussion by Chandrasekhar, who had a vast amount of work on this topic. And also you can see the recent papers. So always in the internet you can see the recent researches on this domain. Okay, in this domain. So mathematically, now the simplest solution is given by this. So where we can write that wz is equal to some w prime z, another function, of course, that's why it's a formal way of writing, another function of z prime, and which is given by equal to w0 sine pi z prime. And if we use that, we can get this Rayleigh number is nothing but pi square plus k prime square whole cube by k prime square. So this is a very simple solution which satisfies this equation, and actually you can check that. Just for your information, this solution is not corresponding physically most of the cases, either in household cases or in or in astrophysical context. Okay, so in both cases actually this equation is nothing but an idealization and can be used for academic purpose, but the philosophy which we will now extract will be roughly the same. Okay, so here for this type of equation I have a Rayleigh number which is given by pi square plus k prime square whole to the cube by k prime square. So this is a function of k prime only. Okay, now evidently now we know that for instability Ra must be greater than, so this is the Rayleigh number for the marginal instability part. Okay, so for instability, okay, as I said, the Rayleigh number, when Rayleigh number goes larger and larger, the system is can be subject to more and more instability. So Rayleigh number can, I mean, when Rayleigh number is greater than this value, this marginal value, then the system is unstable, and for stability, Rayleigh number should be less than this value. Okay, now one can actually plot this marginal Rayleigh number, which you can see in the green line, green solid lines. Okay, and you can see this this is the line which is giving by this RA is equal to, so here in this along this axis RA is plotted, along this axis K prime is plotted, and this curve is nothing but this curve, this one. Okay, this curve. So for a system, now you can easily see that there are two things. One is that, so this solid curve is the curve for marginal instability. If your system has a Rayleigh number, let's say you have chosen a wave number. Let's say wave number is K prime, I mean normalized wave number, K prime is equal to 3. Okay, corresponding to that, if now your system has a Rayleigh number which is superior to the marginal, so for this one, let's say if we just make some drawing for corresponding to 3, the yes, this is the point. So corresponding to 3, the Rayleigh number, the marginals in, the Rayleigh number corresponding to the marginal instability is here. Okay, now if you have a Rayleigh number which is greater than this, then here it should be it should get somewhere here. Okay, and it will have an instability. This is the unstable region. And if your Rayleigh number is less than this value, then you will have stability. Okay, so here you can, for 2 points, 2 arbitrary points, one is in the left of the minimum value and one is to the right of the minimum value. You can actually check this. The same type of behaviors are there. That means for a given wave, normalized wave vector, horizontal wave vector, if your Rayleigh system's Rayleigh number is greater than the marginal stability value of Rayleigh number, then this will be the system will be system will be unstable against convection. If not, the system will be stable against convection. Okay, now this what happens? So if your, so you can see that the this curve will also have something so called a minimum. So if your so this minimum, if you just calculate for this, is called the critical value of the Rayleigh number. So critical Rayleigh number, or RAC. And for such type of solution where RA is equal to this pi square plus K prime square whole cube by K prime square, this marginal marginal Rayleigh numbers. Okay, then the corresponding critical Rayleigh number will be given, actually corresponding critical horizontal wave number will be given by pi by root 2. That means at K prime is equal to pi by root 2, you can have the marginal Rayleigh number to be minimum. Okay, and the corresponding critical Rayleigh number, that is the minimum value of the marginal Rayleigh number, is equal to 27 by 4 pi to the power 4. So which is almost equal to 657.5. Now here there can be a confusion between marginal Rayleigh number and critical Rayleigh number. So marginal Rayleigh number are the Rayleigh numbers, okay, which lie on this curve, and the minimum value of all the marginal Rayleigh numbers for a given system is called the critical Rayleigh number for the system. Okay, now if the system's Rayleigh number lies here, that means, okay, here, Okay, that means that, let's say 300 for example. Okay, that means the system's Rayleigh number is inferior even to the critical Rayleigh number. Then, irrespective of the horizontal wave number, the system is always stable. If the system's Rayleigh number is greater than the critical Rayleigh number, let's say over here, okay, here. I mean, when I am saying now Rayleigh number, that means the normal Rayleigh number. I am not talking about marginal Rayleigh number. I have just, calculated the Rayleigh number of the system, and I am just saying that my system's Rayleigh number is something. Okay, and there you have to take into account this fact that sigma is not equal to 0 in general. Now let's say you calculate your system's Rayleigh number, which is, let's say, 1200 over here. Okay, then what happens? 1200. Then you want to check that whether your system will be stable against RBC or Rayleigh convection or not. Then the thing is that if you start starting from higher length scale, that means lower k value. If you start increasing the length scale, decreasing the length scale, okay, or increasing the horizontal k prime value. So here once again the length scale is in the horizontal direction, because this is the horizontal wave vector. That is something not to be confused with. Okay, that has nothing to do with the vertical dimension. Okay, so this is all about the horizontal size. Okay, if the horizontal length scale is is decreased gradually, that means the horizontal wave number is increased gradually for a system whose Rayleigh number is greater than the critical Rayleigh number. First, it becomes stable, okay, for very small value of k, and then when it just crosses the wave vector corresponding to the marginal Rayleigh number, then it becomes unstable for a range of wave numbers. Okay, and again when it leaves this region from another wave number, okay, another horizontal wave number, of course we are talking in terms of normalized wave numbers k prime, then again the system becomes stable. So stable, unstable, stable. On the other way, if you want to increase the length scale, that means decrease the wave vector, the same thing. First you have a stable region, then you have an unstable region, then you have a stable region. Okay, the system is unstable only for a certain range of wave vectors. Okay, this is very crucial to understand. Interestingly, the onset of RBC at marginal instability can be identified in practical cases, okay, by the appearance of convection cells, or so-called Bénard cells. Bénard, for the first time in his experiment at 1900, okay, showed the formation of this type of structures. Okay, now this type of structures can see in lab experiments. Actually, even in a tea vessel you can see that. Okay, you can have very beautiful pictures on internet, but here I am just showing you the appearance of this almost hexagonal structured Bénard cells in the lab experiment of a Rayleigh convection. And this type of convection cells, which are called the granules, okay, can also be seen in the solar surface near the photosphere, and that exactly confirms the existence of convective instability and the Rayleigh convection actually near the solar surface. Okay, so this makes the whole phenomena astrophysically very much important and interesting. Okay, thank you very much.